For this problem, we're given a parametric curve. We're asked to calculate the first derivative and the slope, the second derivative and the concavity, and finally, whether we have a relative maximum or minimum, or neither, at the point t equals 6. So let's start with the first derivative. That is, let's determine dy dx as a function of t, and then find the slope of the parametric curve at the point t equals 6. So we start with our parametric curve, and one thing that I want to remind ourselves is, what is the derivative dy dx in terms of t? Well, that's just the derivative of y with respect to t divided by the derivative of x with respect to t. So there's two things we need to calculate. We need to calculate the derivative of y with respect to t, and then the derivative of x with respect to t. Let me start with derivative of y with respect to t. Write down the function y equals negative 5t cubed plus 45t squared. Take the derivative of y with respect to t, and this is just a polynomial function, so we'll just use the power rule for derivatives, and that's going to be negative 15t squared plus 90t. This is the numerator for our function dy dx. So that's negative 15t squared plus 90t. Now let's take a look at dx dt. We write down the function x equals 2t squared, the first part of our parametric curve. And the derivative of x with respect to t, well, that's simply 4t. And so that becomes the denominator of our first derivative. Now, I always like to clean up my derivatives if possible. This involves simplifying. I notice that t can actually be a common factor, or is a common factor for the numerator and the denominator. So I'm going to pull out a t from both numerator and denominator, cancel that right out. So we're going to assume that as long as t is not 0, our derivative is negative 15t plus 90 over 4. So that means our first derivative, written as a function of t, would be negative 15t plus 90 over 4. Now, if I wanted to find the slope of the curve at t equals 6, well, let me use the notation, the derivative of y with respect to x when t is 6. We plug 6 into our first derivative function, and that's going to give us negative 15 times 6 plus 90 divided by 4. Simplify this up a little bit. That's negative 90 plus 90 divided by 4. And that is simply 0, right? So the first derivative at t equals 6 is just the value 0. And that means I have a horizontal tangent, or a possible horizontal tangent, right? Well, I have a horizontal tangent with a slope of 0 when t equals 6. Let's take a look at the second derivative. For the second derivative, we actually want to write down what we know, which is that we have the parametric curve defined by x equals 2t squared, y equals negative 5t cubed plus 45t squared. And we know what we calculated, which was that the first derivative of y with respect to x is negative 15t plus 90 divided by 4. In order to calculate the second derivative of y with respect to x, we want to use the formula which states we take the derivative of the first derivative with respect to t, and then we divide by dx dt. So we have two parts to it. We have our first part, our numerator piece, and then we have our denominator piece. Let's focus in and zoom in first of all on our numerator. The numerator says we want to take the derivative of the first derivative with respect to t. So let's focus in here on our first derivative, dy dx. I think I want to rewrite that. dy dx is negative 15t plus 90 over 4. It's a quotient, right? Or a big fraction. Well, I would rather look at it as a linear function. You can take the 4, which is a monomial, and divide it into each of our terms. That would give us that dy dx is negative 15 fourths t plus 90 over 4, or we could go one more step if we wanted to be a little more rigorous, although it's not necessary, but we could divide that down to have that as 45 over 2. Now, what is the derivative of this function with respect to t? Well, I wrote it this way because this is just a linear function. So that means if I want to take the derivative of this function with respect to t, I'm just pulling off the coefficient on the variable t. So I'm left with the constant negative 15 fourths. So that means the numerator of the second derivative is simply negative 15 fourths. dx dt, well, we can recall this from our first part where we found the first derivative. dx dt is just the derivative of the x piece of our parametric curve with respect to t, and that was just 4t if you remember. So that becomes our denominator for our second derivative. And if we clean it up with a little bit of math, we're going to take this complex fraction, make it more simple. Negative 15 fourths divided by 4t is the same thing as negative 15 fourths times 1 over 4t. And that is simply, and let me write this down here, that means our second derivative is simply negative 15 over 16t. Now we want to evaluate that second derivative when t is 6. So that means we want to take 6 and plug it into our parametric curve, right? So negative 15, into our second derivative for our parametric curve. So when we plug it in, that gives us negative 15 over 16 times 6. Oh, let me simplify it this way. Let me see. Negative 15, so 15 is 5 times 3. And 6 is 3 times 2. And when I write it that way, I can see that my 3's cancel right up, right? And so that means I can simplify this down to negative 5 over 32. So my second derivative at t equals 6 will be negative 5 over 32. Now, for part 3, we're asked if we have a maximum, minimum, or neither at the curve t equals 6, or we don't have enough information. Well, let's recall what we have gathered so far. So far, we know that the first derivative at t equals 6 is 0. That meant that we have a horizontal tangent occurring right there on the parametric curve. So when our first derivative is 0, it means we have a horizontal tangent. The slope is 0. The slope of the tangent line is 0. Let's combine that with the following fact. The second derivative for this parametric curve at t equals 6 is negative 5 over 32. Well, when we have a horizontal tangent, there are 3 things that can happen with our curve, right? We could either have a relative maximum. That's one thing that can happen when you have a horizontal tangent. We could have a relative minimum. That's the second thing that could happen when you have a horizontal tangent. Or we could have what's an inflection point where we have neither a max nor a min because we have a change in concavity from concave down to concave up or vice versa. Now, what category we are in is often determined by our second derivative using the second derivative test. One way that I like to do it and remember the second derivative test is with emojis. And that is, if my second derivative is positive, it means my curve is concave up. If my second derivative is negative, that means my curve is concave down. And if my second derivative is 0, well, that means it's inconclusive. I can't tell if I'm concave up or concave down. So I kind of like to think of it this way. Notice our Notice our second derivative is in fact negative. That puts us in this second case here, where we're concave down. And when we combine that with the fact that we're concave down and there's a horizontal tangent when t equals 6, that puts us in the case where we have a relative maximum occurring at t equals 6. So we can bubble in the relative maximum at t equals 6 for the parametric curve. We could put this into decimals if we wanted to, the curve itself, and look and verify that we have our work correct. And then we're done with this problem. If you have any questions, don't hesitate to reach out.